Hey guys, so today's lecture is going to be over Chapter 2, Section 5, which is all about transformations of functions. So I want to direct you to the notes page, which you can find online. I feel like my notes do a pretty good job of working through this. 2.5 isn't so much like learning how to do a specific math process. It's more about looking at the equations of functions and understanding how they move around within the quadrant system. So there's lots of different transformations. When you think about a transformation, the word transformation means to change or to go from one thing to another. So the transformation of functions is where we take like a basic function and we're going to move it around. We're going to either move it up or down, left or right. We're going to stretch it, or we're going to shrink it, or we're going to flip it. Like we're going to reflect it is what we call those. And so really there's just a bunch of general things that like general forms and that show you how to look at these various functions, and then just kind of memorizing either how they move or understanding that you're going to be using, like you're going to be graphing them. And so you're going to be doing the plotting system a lot if you don't kind of memorize the general gist of how these move around in the tables. So my notes do a pretty good job of giving you the basics, but I also wanted to show you in your math book online on page 283, there are these common graphs, or sometimes they're referred to as basic functions or mother functions. And they're very good. There's 7 of them. These you may want to memorize. These are the most common standard functions that you're going to face in this class, and potentially in most of your classes, unless you take like a trigonometry class or something like that. There's the constant function, which is just a line at an f, at like a y value. So that's a flat one. And it tells you, even underneath the graph of it, it tells you what the domain is, what the range is, and it tells you if it's an even or odd function. So this is a really nice table. You have your identity function, you have your absolute value. All absolute values are going to look like a V. So that's something to, just having that general shape in your mind so that when you encounter that function later on, you will have, oh yeah, I know this is going to look like a V. Now, how's it going to shift around? Or am I stretching it or shrinking it? Am I flipping it? But I know it's still going to look like a V even if I do these things. So having that in your head will be helpful. So while I don't expect you to memorize like everything on this chart or anything like that, just having a generalized picture definitely will help you in the long run. There's the quadratic, which is x squared. There's the square root and what that looks like. There's the cubic, and then there's the cube root. So those are definitely very helpful basic graphs. And so I note that on the notes page, but I also wanted to actually show you what those are. And I'll probably flip back over here as we encounter these functions so you can see the general forms. But if we go to our notes page, the very first type of transformation we are going to talk about is a vertical shift. Vertical shifts are where your graph is going to either move up or down based on like its general starting position. And so these are going to look like y equals f of x plus c. Notice this plus c is kind of tacked on at the end. It's not inside of our function. It's just kind of added on at the end. And what that tells us is that we're moving the f of x, the function, we're going to move it up c units. If it's a minus c at the end, then we're going to move it down c units. And I give you a very generalized example right there in the notes, where it shows you that the basic function starts right there close to the x-axis, and then we moved up c units if it was plus c, or we moved down c units if it was a minus c. And we're actually going to do a specific example where, and hopefully, yes, you can see that. I'll make my screen a little bit bigger if it will let me. There you go. So we're going to do a specific example where we're doing f of x equals the absolute value of x, the absolute value of x, and then our g of x is the absolute value of x minus 4. So let's pop back for just a second. Maybe if it's gonna let me, I gotta move this down just a tiny bit because it keeps popping up. So we're gonna do the absolute value of x. So the absolute value of x is right here. That's our v. That's where at 1, 1 we have a dot, at 2, 2 we have a dot, at -1, 1 we have a dot, like for our graphing. So I'm going to graph that first because it says to graph f of x equals the absolute value of x. So I'm going to graph that first. And if you didn't know, or you were in a situation where you didn't want to pull up your book, if you don't have this memorized on how to graph the absolute value of x, then what you would have to do is the plug and chug method or the point plotting method, where you make your graph or your table, where you have your x values and you plug it into your function to get out your y values, and then you plot those points. So that's how you'd have to do that, which is why I do recommend memorizing some of the general functions like this, so that you don't have to make this table over here and think through every single point. So, so there's the f of x. So f of x is going to be in yellow. I don't know if you can differentiate the colors. Hopefully when I get the next color up, you will. And then it says it wants us to graph g of x, where it is the absolute value of x minus 4. So notice we have our function, the regular function that we had. We have our f of x right there. And then we have this minus 4 tacked on at the end. That is how you know it's a vertical shift. Here in a minute, you'll see the difference between a vertical shift and a horizontal shift. So it's very important to go ahead and note vertical shifts are tacked on outside of the actual function. Okay? So that vertical shift, it says minus 4. That means for every single value on my graph, I'm going to go down 4 units. So instead of having the point 0, 0, I'm now going to have the point 0, -4 down here. And instead of having 1, 1, I'm going to have 1, -3. And instead of having 2, 2, I'm going to have 2, -2. What I did is I added, or I subtracted 4 from all of my y values. That's how I'm doing my vertical shifts. You're changing your y values. And then the purple is my g of x. If it would have said plus 4, then I would have gone up 4 and had a different v up here instead of going down 4. So vertical shifts work very logically in that you're going down. You're going more negative because it says negative, and you're going more positive when it says positive. Okay, that's vertical shifts. See, there's my graph in my notes. So if there's vertical shifts, there's also horizontal shifts. And these maybe are a little backwards than what you're thinking. In that when we had a vertical shift and we had plus c, it means we went up. When we have a plus c for our horizontal shift, notice that is inside of our function. It's not outside of our function. Up here, out here, our vertical shift, see, it says the function plus c. Horizontal shift says f of x plus c, so that c is inside of our function. And so if you have y equals f of x plus c, this is a horizontal shift of the function, but it's to the left 3 units. So it's backwards. You're going to go negative if it says plus c. If it says minus c, you're going to go positive. And so that is very backwards from what you're probably thinking. Because vertical shifts, logical, plus c goes up, minus c goes down. Here, if you have a plus c, you're moving to the left. And if you have a minus c, you're moving to the right. So once again, I did a general example to show you where I did the plus c and I moved to the left c units, and I did minus c, and I moved to the right c units. The biggest thing to remember though is if it's inside the function, then it's a horizontal shift. If it's outside the function, it is a vertical shift. And so I'm going to do a specific example. F of x equals the square root of x, and g of x equals the square root of x, and I said plus 5. Okay, so once again, I'm going to flip back over to our textbook because I want you to see the general equation for the square root of x. That is the standard square root, or the square root function. So that's where if I had 1, I'd have 1, and if I had 4, I'd have 2. And so that's kind of the important thing about the square root. Again, if you're not sure, then you can do the plug and chug method. The one thing about the square root, obviously, if you look at the picture, is you don't have any negatives. And that's because we don't take the square root of negative numbers in general. I mean, we've learned about I and imaginary numbers, but in general, we do not take the square root of negative numbers. And so if you plug in -1 or -2, you're not going to get out a number that you're going to be able to graph on your coordinate system. So that's something to note if you have to do the point plotting method. So we have 0, 0, we have 1, 1, and then we would have 4, 2, and that's my f of x. That's the general form. Now I need to plot my g of x, which says f of x, like it's got my x plus 5. So it's plus 5, that's a horizontal shift, but I'm going to the left 5 spots, 5 places. So instead of 0, 0, I'm going to go 1, 2, 3, 4, 5, and I'm going to have -5, 0. Horizontal shifts affect your x values. So you're shifting your x's to the left 5 spots. So I'm going to go 1, 2, 3, 4, 5, and have -4, 1. Then I'm going to go 1, 2, 3, 4, 5, and have -1, +2. Make that a little bigger so that it covers that spot. So this one is my g of x. I took my f of x and I moved the whole graph to the left 5 places. If it would have said square root of x minus 5, I would have shifted everything to the right 5 places. Okay, so those are horizontal shifts. Those are inside of the function and they affect your x values. Vertical shifts are outside the function and they affect your y values. Again, there's my nice graph in my notes. Now, what if we are going to combine horizontal shifts and vertical shifts? So we're going to do 2 and in one graph. Well, it's not any harder. You're just going to have, I don't know, in the beginning, I kind of recommend having an in-between, and I'll show you what I mean, like an in-between graph. So we need to graph x squared, and then it wants us to graph x plus 1 squared minus 3. Okay, so if you look at just our g of x, that's kind of our final resting place. That's where we want to go. You notice we have an x plus 1 inside of our function. So that tells me there's a horizontal shift. We also have this minus 3 out here though. That tells me there's a vertical shift. So I'm going to have two different shifts going on in this same graph. But I'm starting from the same starting point. I'm starting from f of x equals x squared, which is your quadratic. That's your U-shaped function. So I have the point 0, 0, and I have the point 1, 1. I have the point 2, 4, negative 1, 1, and negative 2, 4. So that's my f of x. Okay. While you are still learning how to do these vertical and horizontal shifts or any of these transformations, I do recommend a lot of the in-between steps. So instead of jumping straight into g of x, where I do both my horizontal and my vertical shift, I'm going to just do my horizontal shift first. So that means I'm going to have this extra picture, my h of x, where I'm just doing x plus 1 squared. That way I'm really only doing one shift at a time, and I can keep that really straight in my head. So instead of going straight to g, I'm going to do this h of x first. So I'm going to shift to the left one place because it says x plus 1 quantity squared. So I'm going to shift every point on my graph to the left one spot. And this is another reason why I like to graph these in-between stages, is because then I don't have to do any tables or anything like that. If I've got my general form on my graph, I can just start shifting using the points that I already have. So if you're a visual person, that may be very helpful for you. If you are not a visual If you are not a visual person, then maybe you do want to do the tables and the point plotting method, and you want to do it that way. It's totally fine, whichever way you would like to do it. So I started with my f of x. I shifted everything to the left one place for my h of x. So I've gotten this part done. Now I need to do my -3 for my vertical shift. I did my horizontal shift. Now I need to do my vertical shift. So I don't start back here at the original equation or the original picture. I'm going to start with my h of x picture because I already did my horizontal shift. So the only thing left is the vertical shift. So I'm starting with my purple graph, and I'm going to shift everything down 3 units because it says -3. So I'm going to go 1, 2, 3, 1, 2, 3, 1, 2, 3. 1, that was weird. So this bottom one, or this orangey, peachy one, is my g of x. That's the final one. So from going from yellow to orange, I shifted to the left one, and then I shifted down 3, and I get to this final one. In my notes, I used graphing paper so I could show you this middle step as well, where I graphed the original just in pencil. I graphed the horizontal shift in the red pen, and then I highlighted the final answer, the final shift that includes the vertical shift. So if you're doing both vertical and horizontal, always do the horizontal first and then do the vertical. You can think about it as like order of operations. You always start kind of in the middle with your equation or your function, and then you work out. So horizontal shifting happens more internally because it happens inside the function. And then the vertical shifting happens kind of at the end. It's tacked on at the end. So that's vertical and horizontal. You can do them separately. You can do them together. That's 2 types of transformations. There's also reflections, and we're going to discuss really 2 types of reflections where we reflect about the x-axis and we reflect about the y-axis. So if we are reflecting about the x-axis, you can think about folding your graphs this way, where the x-axis is your folding line. And so you have a graph on top or you have a graph on bottom, and when you fold it, where does that lay on the other half? So that's what it means to reflect about the x-axis. In general form, what we say is y equals negative f of x, so we have the negative function, is the graph of y equals the regular function reflected about the x-axis. So if the functions are the same, but if you just stuck a negative outside of it, then you have a reflection about the x-axis. And so I have a specific one that will work. Sometimes, I will just go ahead and say this, sometimes transformations are hard for students because they are very visual, and you do have to kind of recognize these rules. If that is the case for you, the best thing you can do is to practice. It's to pull open the notes and pull open the quizzes or the homework and to just do a whole bunch of them so you get more comfortable with them. Okay, so make sure you allow time to actually play around in this section a little bit. Oh, do I need to go out further? Yeah, I kind of need to go out further. 5, 6, 7, 8. 5, 6, 7. I just want to be able to show you more than one point. Okay, so it says that we need to graph the cube root of x. So I'm going back to my general functions and I'm looking, and here's my cube root of x. So it looks like the cubic, but on its side, which is exactly what happens with our square roots and our standard quadratics, is it's really just on its side. So again, if you don't want to go back and look at that all the time, you just do the point plotting method. Which is really what I do. I just do it in my head instead of doing it on the graph so much. So I say, well, the cube root of 0 is 0. The cube root of 1 is 1. The cube root of, this is where you have to think about what do we take cube roots of? We take cube roots of perfect cubes. So the next perfect cube is an 8. 8 is 2 times 2 times 2. So I go out to 8 and I go up to 2. So there's that. But the cube root, you can have negatives because it's a cube root. Negative 1 times negative 1 times negative 1 will give me negative 1. So I can have that over here. Negative 2 times negative 2 times negative 2 will give me negative 8. So I can have that out here. All right, so there's f of x. That is just the standard equation, the standard picture for the cubic root of x. But I need to do g of x where it's negative the cubic root of x. So that negative, notice, is just outside of the function. When it's outside of the function, we are doing a reflection about the x-axis. So one way to think about this is we're folding our axis this way. So everything up here is going to be down here, and everything over here is going to be up here. What we're really doing is we're negating our y's. So you probably want to write that down. You are negating the y values when you're doing a reflection about the x. So what that means is that instead of having 1 positive 1, if I'm negating my y's, I'm changing the sign on my y's. So I'm going to have 1 negative 1. Instead of having 8, 2, I'm going to have 8 negative 2. Instead of having negative 1 negative 1, I'm going to have negative 1 positive 1. Instead of having negative 8 positive, or negative 8 negative 2, I'm going to have negative 8 positive 2. So that this purple is my g of x. So it goes this way. What I did is I folded my graph along my x-axis and it's reflected. You can memorize that it negates the y's. I think that is super helpful. You can also always, like I've said, just do the point plotting method. That takes a lot longer, and I feel like you're more likely to make mistakes than if you actually start recognizing some of these little tricks. So reflections about the x-axis, you negate or change the sign on your y values. So that's kind of different. You're reflecting about the x, so you're changing your y's. There's my graph on the notes. So if we reflect about the x-axis and we change our y's, when we reflect about the y-axis, we're changing or negating our x values. So it's flip-flopped. Again, notice that the reflection about the y-axis, it's a negative x inside of our function. When we reflected about the x-axis, that negative was outside of our function. And so that's kind of how you tell them apart when you're just looking at the general forms. I'm going to erase and make my specific example graph ready for you. Okay, so we're going to do a specific example that shows a reflection about our y-axis. So instead of folding our graph or our paper this way, we'd be thinking about folding our graph or paper this way. So anything that's over here is now over here, or anything that's over here is now over here, or vice versa. So when we are doing reflections about the y-axis, you are negating your x's. So I'm going to draw f of x, which is the square root of x. That's where we have 0, 0. We have 1, 1. We have the square root of 4 is 2. And that's all we had because we don't have the square root of negative numbers. So this is our f of x. Okay. But we need to reflect this about our y-axis. So we need to fold our paper over and reflect the graph. And what we're doing then is we're changing our x's. So if they have positive values, we're changing them to negative values. We do not change our y's when we are reflecting around our y-axis. So instead of having 1, negative 1, I'm going to have, or excuse me, 1, 1, I'm going to have negative 1, 1. I'm changing the sign on my x value. Instead of having 4, 2, I'm going to have negative 4, 2. Changing the sign on my x value. 0, 0 stays the same. And there is my g of x. This is one of those very specific examples where if you did the table method, it's going to be very confusing because you would be plugging in the square root of negative 1. Well, you don't want to do that. How do you graph that on the same coordinate system when you don't have imaginary numbers? So that's one of those times where it's actually very important to understand what's happening in your graph and how to make that transformation without using the point plotting method, because it's not always going to give you a really nice answer. So if you are reflecting about the y, you are changing your x's. You're leaving your y values alone. Okay. Again, here's my graph in my notes. So we've done 4 different transformations so far. We have done vertical shifts where you move up or down. We've done horizontal shifts where we move left or right. We've done reflections about our x-axis where we fold downward and we change our y values. We've done reflections about our y-axis where we fold side to side and we change our x values. Now we have vertical stretching and shrinking. So we're going to stretch this way, or we're going to compress or shrink this way. Stretch it or shrink it. This is where we have a constant out front of our function. So if our constant, or our c, is greater than 1, then we have y equals c times our function, is the graph of y equals f of x, so it's our function, vertically stretched by multiplying the y coordinates by c. So when you are stretching and shrinking vertically, you're changing your y values. And so you're taking your y values from your original, multiplying all of them by c and stretching them this way. If we have our c is between the values of 0 and 1, so it's a fractional point, part of 1, then our stretched graph or a shrunk graph is the original that is vertically shrunk by multiplying the y coordinates by c. So instead of stretching, you're getting smaller and smaller, so our graph is going to shrink. So we're actually going to do both so that you can see how this works. We're going to do a stretching and a shrinking, all on the same graph as the original. So we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Okay. So for this example, we are graphing f of x equals the absolute value of x. Again, absolute values always look like a v. We've already done this. So I'm just going to graph that one in general. So we would have 0, 0. We would have 1, 1, 2, 2, 3, 3, negative 1, 1, negative 2, 2, negative 3, 3. And we have this nice v as our f of x. So that is just the original plain J, no stretching, no shrinking function. Now our g of x says we have 2 times our x, our f of x, or 2 times our absolute value of x. So that is a c, there is 2, and it is greater than 1. So it's this first example where we're going to be vertically stretching our graph. And what it says is we're taking each y value that we have in our original and we're multiplying it by our c, which is 2. That's what we're doing for all of these. You're taking your c, multiplying your y's, and changing them. So our x values do not change. So I still have x is 1, but instead of y equals 1, I multiply that by 2, so it's y equals 2. Instead of y equals 2 here, it's going to be y equals 4. Instead of y equals 3 here, it's y equals 6. And it's the exact same thing for the other side, just because this is a very symmetric graph. And then all the way out here. That's g of x. Notice on the picture, we have a regular, and then when we vertically stretch it, it makes it kind of like a skinnier, longer V. And that's because we have taken our original V and we're stretching it upwards. Because we did that by a multiple of 2. Now h of x over there says 1/2 times the absolute value of x. So that 1/2 is between 0 and 1. And so what we're doing is we are taking all of our y values and we're timesing them by 1/2, which is going to make them shrink vertically. So instead of having 1, 1, I now have 1, 1/2. Instead of having 2, 2, I now have 2, 1. Instead of 3, 3, I have 3/2, which is 1.5. And 4, instead of being 4, would be 4, 2. Like I'm just adding another point so I can have a straighter line. be the same thing over here. I'd have a half, I'd have 1, I'd have 1.5, and then I would have 2. So this bottom one then is my h of x. So instead of having a nice V, I have squished it. I tried to press down on it. And when you press down on it, it causes it to go out flatter like that. When I pulled up on it to vertically stretch it, it went like this. And when I compressed it or I shrunk my y values. And so it went out flatter like that. So vertical stretching, you go up. Vertical shrinking, you go out further. You smush it down. But did we do the process any differently? No. We still took our C and we multiplied our y values to get our new y values. It didn't matter if the C was greater than 1 or if the C was between 0 and 1. We still did the same thing. I took all my y values times 2 for my g of x, or I took all my y values times a half for my h of x. So it did not change the process. Again, in my notes, I have the example that I just did on the board. So I stretched it in red and I shrunk it in the highlight. So if we can vertically stretch and shrink, we can also do that horizontally where we stretch and shrink. And it's going to follow if you notice, when we go horizontal, we kind of do the opposite. Like we added C horizontal shifts. So that meant we went to the left C instead of to the right. Same thing happens with horizontal stretching and shrinking. It's going to do kind of a backwards thing than what you think. So when C is greater than 1, we have f of C times x is the graph of horizontally shrinking instead of stretching. You're going to shrink by dividing the x coordinates by C. So instead of making it bigger, we're actually making it smaller. And then when our C is between 0 and 1, we're dividing by the x coordinates and we're getting bigger C's. So we're going to shrink it if the C is greater than 1, or we are going to stretch it if our C is between 0 and 1. All right, this one, I give you an interesting f of x because you won't always be given a general function like a quadratic or an absolute value. So I wanted you to see an example where you get just a whatever function they give you. So we're going to graph f of x, and then we are going to graph g of x, where g of x equals f of 2x, and h of x, where that's f of 1/2. So immediately just looking at these, you should know that we're going to do horizontal stretching and shrinking because the C's are inside of your function, whereas when it was vertical, the C's were outside. When you're doing anything vertically, it's always outside the function. It's always tacked on at the end, or it's a constant out front. When you are doing horizontal shifting or transformations of any kind, it's always inside the function itself. So let me show you what I mean. Here is our graph. No, that'll be fine. Here is our f of x. This is the one that they're going to give you. So this is the point -4, 0. This is the point -2, 4. And we have 0, 0 right there in the middle. Then we have the point down here, which is 2, -2. And then we have the point over here, which is 4, 0. So this doesn't follow any of our regular rules. It's not a general standard equation or standard function in any way. But they can give this to you, and you can do all kinds of transformations. You should be able to do any transformation that I give you. If they give you a graph just like this, because all you're doing is manipulating the points around. We're just moving the points. And so that's what I wanted you to see with this example. Okay, I gotta make my table for you guys. One, 2, 3, 4, 5, 6, 7, 8. Okay. So that one over there is my f of x. This is my f of x. Now I need to find my g of x, which is f of 2x. So that's my c. My c is 2. If my c is 2, then what I'm doing is I'm dividing. I'm shrinking horizontally my x coordinates by dividing them by c. So I'm going to look at my first point. It was negative 4, 0. So if I'm dividing my x values by 2, then I'm going to have negative 2, 0. Notice my y didn't change, just my x changed. So I have negative 2, 4. If I divide that by 2, if I divide my x value by 2, I have negative 1, positive 4. 1, 2, 3, 4. Right there. Again, my y value does not change, just my x. 0, 0 is still going to be 0, 0. So it's in there. So there's the first half of my graph. Now I have this v part where I had 2, negative 2. I'm dividing my x by 2. So I have 1, negative 2. And then 4, 0. Divide 4 by 2. And I have 2, 0. So this is g of x. I took my f of x and I shrunk it horizontally. I squished it together this way by dividing all of my x values by 2. Now for my h of x, I have f of a half x. So this is the second type. So if I'm not shrinking, I'm stretching. So what I'm doing is I'm dividing all my x's by 1/2. If you divide by a fraction, that's where you flip it over and you're multiplying. So instead of dividing by 1/2, what I'm really doing is I'm multiplying all my x values by 2. So instead of having negative 4, 0, I'm going to have negative 8. 1, 2, 3, 4, 5, 6, 7, 8, 0. Negative 2, 4. I have negative 4, 4. 0, 0 stays the same. So there's that first half. I would have negative 2, or 2, negative 2, so that'll be 4, negative 2. So it's out here now. And then I would have 8, 0. 1, 2, 3, 4, 5, 6, 7, 8, 0. And that is my h of x. So notice it takes up a lot more room because I stretched it horizontally. None of my y values changed at all. So I didn't go up or down any further on my transformed ones than I did on my original ones. All I did was I either compressed it or shrunk it in x-wise, or I stretched it out x-wise. Okay. So here's my, there's the f of x, and then there's my general. I actually think my graph on the board turned out better because it doesn't have quite as pokey, I have more of a rounded graph on the board than I do on here. So those are all the different types of transformations, and you can do all of them all in one thing. You do need to follow a specific order if you're going to do them. Earlier when we did vertical and horizontal shifting, we did the horizontal shifting first, then we did the vertical shifting. So there is kind of an order of operations when it comes to transformations. And that is what is on the notes right there, where you're going to do your horizontal shifting first, Then you're going to do any of your stretching and shrinking that you have. You're going to reflect either about the X or the Y value or axis if you have that. And then at the very end is when you do your vertical shifting. And you can, it does make sense as to why we do what we do. When we look at the equations that we're going to be graphing, you're really starting on the inside and you're working your way out, which is how we solve equations. Is we start, we do exponents and parentheses first, and then we keep working our way out and out and out. And that's what we're doing when we're graphing these transformations. So I'm going to graph f of x equals x squared and g of x equals 2 times x plus 3 squared minus 1. So before we did a lot, like we just went from our graph to our graph. The way that I'm going to show you to do this is I'm going to do 4 different graphs, and then to show you the transformational steps. I do recommend that in the beginning so that you're not getting completely lost on what you're doing. So the very first thing I'm going to do is I'm going to graph just the f of x, which is x squared. So I have 0, 0, I have 1, 1, and I have 2, 4. Negative 1, 1, negative 2, positive 4. And it's my quadratic. So this is my f of x. This is my starting point. Before I do any transformations, I start here. Then it says I'm going to do horizontal shifting. Horizontal shifting was where we had f of x plus 3. Like we had f of x plus 3 or something like that. And that told us to move our graph left or right by so many units. Well, and actually in this case, we have the plus 3. So we are going to shift. If it says plus 3 and we're horizontal shifting, that means we're going to the left 3. One, two, three, four. 1, 2, 3, 4. Yeah, that's enough. So instead of 0, 0, I'm going to move that to the left 3 spots. 1, 2, 3. Oh, I guess I should go one more spot. Instead of 1, 1, I'm now going to move that to the left 3 spots. 1, 2, 3. 2, 4. Or sorry. Yeah, 2, 4. 1, 2, 3, 4. I'm now moving to the left. 1, 2, 3. Move to the left. Move to the left. So here's what my graph looks like after I've done the horizontal shift. So I started with f of x. Now I've shifted it. I've done this part right here. I have shifted it to the left 3 units. Okay, so that's horizontal. Now I need to look, is there any stretching or shrinking going on, whether it's horizontal stretching or shrinking or vertical stretching or shrinking? Well, I do have that too out front. Because it is out front, that tells me that that is vertical stretching or shrinking. Vertical says that if this is greater than 1, then I'm multiplying all my y values by that number. So I'm not going back to the original now because we've done a transformation. So I'm going to start with this graph that's already been shifted horizontally, and I'm going to multiply all my y values by 2 to get my new graph. Okay. 1, 2, 3, 4. Okay. So I have the point 1, 2, 3, negative 3, 0. 1, 2, 3. So negative 3, 0 stays because 0 times 2 doesn't change. I had the point -2, 1, but I'm going to multiply that 1, that y value, by 2, so it's going to come up to -2, 2. I had the point -1, 4, but instead of it being -1, 4, I now have to multiply the y value for that by 2, so that will be -1, 8. I do the same thing for the other side. Luckily, this one's symmetric, so usually once you do one side, you can think about just reflecting it, and that makes it easier. So now I have stretched my graph vertically. So I've shifted my graph horizontally, I have stretched my graph vertically. Is there any reflecting? No, we don't have a negative inside of our function. We don't have a negative outside of our function, so there's absolutely no reflection. So the only thing that we have left to do is this vertical shifting. Then it's a -1. So what that means is I'm going to have my graph from right here, and actually I'm just going to do it on the same graph. I have the last graph that I had after it's been shifted horizontally and after it's been stretched, and now I'm going to move everything down by 1. It's a vertical shift, so I'm moving everything down by 1. So instead of 0, oops. Instead of 0 or -3, 0, I'll have -3, 1. Move this down 1 point, move that down, and it's not supposed to go through that graph. That's just where I didn't graph very well. Again, this is just where I didn't graph very well. So imagine that my graph is better, and I'll show you on my notes that my graph is better. So this orange one is my g of x. This very last one that you graph is all of it. We have shifted it horizontally, we have stretched it vertically, and then we have shifted it vertically. And those are the only 3 things that our example asked us to do. We did all 3 of the things that our example asked us to do. And so on my notes, I have the original, and then I tell you I'm going to horizontally shift it to the left 3. Notice I do a little arrow showing me I'm going to the left 3. Maybe that works for you, and that's what you need to do. So then I shifted it. Then I noted that I'm going to stretch it. And then once again, I noted that I'm going to go down by 1 to where here's my final graph. In the beginning, while you're learning how all of these different transformations work, I really strongly do recommend doing these multiple graph situations. You can get yourself a graphing, like a notebook that has graph paper. At Walmart, they actually make, how I did it here is they have sticky notes you can order on Amazon, like Post-it notes that are graph paper. And so I just did that and I stuck them in my notebook. You can also always just use regular paper. Obviously, I did a pretty good job just on the board, but I do recommend doing that. You can also just print off graph paper. The only thing with that is that it's usually really dark, and so you might have to use a marker or a color to indicate what you're doing. Obviously, I don't see your notes because it's online, like your homework and things like that. So I won't know how you're doing it. But to stay organized and to follow the transformations as you progress through, I do recommend doing that. Now, some of you may be saying, well, if I'm using the point plotting system, couldn't I just have my table and do that? You can. You absolutely can. But again, with some of them, like this was with a quadratic, so there's not really any tricky parts that's going to mess you up. If this had been a square root, though, and then you had negative numbers in your square root, you're not going to get the full graph by doing that. So I do recommend, don't try and take shortcuts. Math isn't about taking shortcuts. Math is about learning the math. So I recommend learning the process of how you do these shifts and these stretches and shrinks. Play around with it. Use your homework. On the homework in the bottom of the problem, after you've solved it, will be a similar exercise button. click it. Do a similar exercise. Make sure you understand what you're doing and how all of these different shifts happen. That way you can do the best you can when it comes time to the home or to the quizzes and the test. Okay? So that is 2.5. That is all of the different types of transformations that we will do with a function. We did vertical shifts, up and down. We did horizontal shifts, left and right. We did reflections about the x-axis where we would fold our paper this way. We did reflections about the y-axis where we'd fold our paper this way. We did horizontal stretching and shrinking. We did vertical stretching and shrinking. And then we did them all together. So that is everything we covered. Please play around with it. And remember, always come to me if you have questions. So thank you. Have a good day.